Hello everyone, this is the first video of a playlist about the preparation of imidazoles. I've organized the most relevant strategies into 3 parts. In this first video we'll have a look at the properties and uses of imidazoles and at their preparation by cyclocondensation. This strategy gives easy access to a broad variety of substituted imidazoles. The video is a bit long, but you're of course welcome to skip to the section which interests you most. In part 2 I'll show you examples of the preparation of benz imidazoles, and part 3 is about chemical transformations of imidazoles by substitution of hydrogen, for instance halogenations, nitrations, alkylations or arylations, both at carbon and at nitrogen. Imidazole is thermally and chemically stable because of its high degree of aromaticity. It remains unchanged at 600 degrees Celsius or when heated with 8 molar aqueous caustic. Unlike substituted benzenes, however, the ring cleavage of imidazoles is facilitated by electron-withdrawing or donating substituents. Because of their stability and easy preparation, imidazoles are important structural elements of drugs and biocides, sometimes as pharmacophore, but often just as a more passive scaffold. The high chemical stability of imidazole correlates with its calculated resonance energy, for instance the Dewar resonance energy. This is the difference between the standard enthalpy of formation as determined by combustion in a calorimeter and the calculated enthalpy of formation of a hypothetical compound with localized double bonds. As shown here, pyridine and imidazole are highly aromatic, while thiophene, pyrrole or furane are much less stabilized by aromaticity. Oxidizing benz imidazoles with hydrogen peroxide in hot concentrated sulfuric acid yields imidazole dicarboxylic acids, without significant degradation of the imidazole ring. And the catalytic hydrogenation of benz imidazoles yields cyclohexanoimidazoles, not diaminobenzenes or imidazolines. Here a huge excess of catalyst was required, probably because of the strong catalyst poisoning effect of imidazole. In particular, aminomethyl imidazoles or imidazoles with other chelating groups bind strongly to metals and can be potent catalyst poisons, even in the presence of acids. The extent of aromatic stabilization also becomes clear when comparing imidazole with 1,2-diaminoethylines. The latter are still more reactive than simple enamines and quickly react with oxygen at room temperature and are difficult to handle and to purify. Imidazole, on the other hand, despite its diaminoethylene substructure, is much less nucleophilic than enamines and perfectly stable at the air. Imidazole can be nitrated in fair yield at position 4 with a hot mixture of nitric and sulfuric acid. 1,2-diaminoethylines, however, are similarly hypergolic as hydrazines and ignite spontaneously when mixed with nitric acid, even at -40 degrees Celsius. Unsubstituted imidazole is both a weak acid and a weak base. In water at around pH 7, imidazole is 50% protonated and 50% neutral, while deprotonation will first occur at around pH 14. Particularly remarkable is the acidity of imidazolium salts at position 2. These salts have a pKa of 24 and can be deprotonated in aprotic solvents to yield diaminocarbines. Thus, imidazolium salts are more acidic than methanol. Diaminocarbines form strong bonds to late transition metals, but can also dimerize to tetraaminoethylines. Imidazoles are similarly nucleophilic as pyridines and less reactive toward electrophiles than tertiary amines. Here you can see the relative rates of quaternization by methyl iodide and acetonitrile. The nucleophilicity roughly correlates with the basicity, as would be expected. A few imidazoles are prepared on a large scale, but not as large as pyridines. The main industrial application of imidazole, methylimidazole and ethylmethylimidazole is as hardener and catalyst for the manufacture of epoxy resins. Methylimidazole is also a key intermediate for the preparation of ionic liquids. The 3 imidazoles shown here are prepared from aldehydes and ammonia. Because of their high stability, imidazoles often form easily, sometimes even if the cleavage of CC bonds is required. I'll show you some examples later. Under optimized conditions, the synthesis shown here proceeds cleanly and in high yield, despite the many potential side reactions. Histidine is a proteinogenic amino acid manufactured mainly by extraction from protein hydrolysates or by fermentation. Enzymatic decarboxylation yields histamine, an important neurotransmitter. Histamine binds with high affinity to 4 receptors, and there are selective agonists and antagonists for all these receptors. Histamine H1 receptor antagonists are the classical antihistaminics for treating the symptoms of common cold, hay fever, and other allergies. Diphenhydramine, for instance, is a selective histamine H1 antagonist and has been used since 1946 to suppress the symptoms of airway infections. Histidine is sometimes found at the active site of enzymes. In proteases, for instance, the imidazole substructure of histidine serves as a proton relay to enhance the nucleophilicity of a serine hydroxy group. Many drugs and plant protection agents are substituted imidazoles, like those shown here. In cimetidine, the first selective histamine H2 antagonist suitable for the treatment of stomach ulcers, the imidazole ring is a critical pharmacophore and difficult to replace by less basic heterocycles. In losartan, however, the important pharmacophore is the biphenylyl tetrazole, and the imidazole fragment is less critical than in cimetidine. Miconazole is a typical azole antifungal, and the imidazole ring can often be replaced by triazoles without much loss of potency. Okay, let's see how we can prepare substituted imidazoles. Formal hydrolysis of imidazoles would yield an alpha-aminoketone and a carboxylic acid. In my videos about the preparation of phenethylamines, you can find a thorough discussion about how to prepare aminoketones and about their properties. Because aminoketones are unstable, most imidazole syntheses are based on other precursors, such as haloketones, oxyminoketones, or nitroketones. And because imidazoles are formed readily, even precursors that require oxidation or reduction can be used to prepare imidazoles. Also for the carboxylate fragment, many different synthetic precursors are viable. For instance, amides, amidines, iminoethers, aldehydes, nitriles, and even alcohols or amines. From a given aliphatic aldehyde, 3 different types of imidazole can be prepared. In some strategies, the aldehyde may just act as a precursor to the carboxylic acid fragment and will be oxidized by hydride abstraction or tautomerization. Then, in the presence of amines or ammonia and tosmic, imidazoles as those of the second equation can be formed. I'll show you the structure of tosmic in a minute. Finally, in the presence of halogenating or other oxidizing agents, aldehydes can be converted into alpha-aminoaldehydes and then cyclized to imidazoles as shown in the last equation. These same imidazoles can also be prepared from carboxylic acids or ketones. Thus, a given imidazole can often be obtained from different starting materials, and their availability, price, and the attainable yields will determine which strategy is best. I'll show you now examples of the most practical imidazole preparations. I'll start with haloketones, aldehydes, and related electrophiles as starting materials, followed by amino acids, isonitriles, and then alkynes. Most alpha-bromoaldehydes are unstable and difficult to handle. Here, a protected form of brominated malone aldehyde was condensed with an amidine, and mainly one of the 2 possible isomers was formed. Only one isomer was to be expected here, and the yield was therefore higher than in the previous example. A larger excess of chloroacetone would probably have caused quaternization of the pyridine or alkylation of the imidazole, but this was avoided here by using equimolar amounts of reactants. Bromine is easier to handle than chlorine, and bromoketones are therefore often preferred intermediates for the preparation of imidazoles. One typical byproduct of imidazole formation from haloketones are oxazoles. In this specific example, more oxazole was formed with anhydrous than with wet potassium carbonate, probably due to some solubility issue. In this example, the cyclocondensation was conducted in aqueous THF, where both the base and the amidine hydrochloride were more soluble than in anhydrous organic solvents. A high yield of imidazole resulted. Thus, the choice of solvent is important in reactions involving salts. One common way to convert haloketones into imidazoles is by strong heating in formamide. This reaction is assumed to proceed by intermediate formation of a hydroxyketone and then a bis-formamidoethylene. Instead of carboxylic acid derivatives, also aldehydes can be used as C1 precursor of imidazoles. Here, brominated trifluoroacetone was condensed with an aliphatic aldehyde and an excess of ammonia. Interestingly, the initially formed trifluoromethyl imidazole could be transformed into a nitrile by heating with aqueous ammonia and potassium phosphate. As an alternative to haloketones, alpha-hydroxyketones can be used to prepare imidazoles. This example was conducted in liquid ammonia as solvent and under pressure, with an amidine as carboxylate equivalent. Amidines are not readily available and can be difficult to purify and to handle. One alternative are iminoethers, which can be prepared from nitriles, alcohols and gaseous hydrogen chloride. Here, thionyl chloride was used as hydrogen chloride source. Condensation with an alpha-hydroxyketone, again in liquid ammonia, yielded the expected imidazole. The required hydroxyketone was prepared by hydration of butenediol. In this example, formaldehyde was the C1 component and the electrophilic C2 precursor was an alpha-acetoxyketone. The excess of copper acetate served as oxidant. Also, alpha-aminoketones or various protected forms of aminoketones can be converted into imidazoles. Here, an aminoketone was heated strongly with formamide and the expected imidazole resulted in fair yield. In this example, an acylated aminoketone was condensed with the primary ammonium benzoate by refluxing an heptane for 2 days. The protective groups of the resulting statine intermediate remained unchanged. Here, a protected aminoketone was condensed with an iminoether. The latter had been prepared from a nitrile and methanol under alkaline conditions, but this strategy only works well with electron-deficient nitriles. Normally, acidic conditions are required to prepare iminoethers from nitriles. All the protective groups were removed by heating with concentrated hydrochloric acid. One potential side reaction was hydroxymethylation or chloromethylation of the phenol at carbon with the formaldehyde fragment of the alkoxymethyl protective group, but this did not occur here. In this example, an alpha-amino-oxime was generated by Michael-type addition of aniline to an acrylate. Condensation with formaldehyde then yielded a substituted imidazole. Similarly, alpha-aminohydrosones can be cyclocondensed with aldehydes to yield imidazoles. Protected aminoketones or aldehydes can be added directly to nitriles and then cyclized to imidazoles. Unfortunately, nitriles are poor electrophiles and do not readily react with nucleophiles. Usually a two-step strategy, where the nitrile is first converted into an iminoether followed by reaction with the aminoketone, is a more robust strategy. Here, formation of the intermediate amidine required an excess of copper chloride, which had to be removed from the product by precipitation with thioacetamide. Instead of aminoketones, also alpha-amino acids can be converted into imidazoles. In this example, cyclization of the intermediate amidine by intramolecular acylation would have yielded an imidazolinone, but with the Wiltzmeier reagent, both deoxychlorination and formylation of this imidazolinone occurred. Similarly, acylated alpha-aminonitriles can be cyclized to imidazolinones or halogenated imidazoles. In this example, the dehydrating reagent was a mixture of carbon tetrachloride and triphenylphosphine. Here, cyclization of a cyanomethylamide and nickel-catalyzed phenylation of the imidazolinone occurred in one step. Condensation of alpha-hydroxyminoketones with aldehydes and ammonia should yield N-hydroxy-imidazoles. In this example, strong heating led to the formation of the non-hydroxylated imidazole, either by ring fission and displacement of hydroxylamine by ammonia or by direct reduction with ammonia. Heating benzylamine with 1,2-diketones can also yield imidazoles, as in this example. Formation of the intermediate imidazoline required tautomerization and a formal oxidation of benzylamine. The final dehydrogenation occurred spontaneously upon heating in DMSO. Because of the high aromatic resonance energy of imidazoles, imidazolines are powerful reducing agents and readily release hydride or hydrogen. Also, secondary amines can react with 1,2-diketones to the corresponding imidazoles. Here proline was condensed with benzyl, but in principle other secondary aliphatic amines should also react this way. In this example, a 1,2-dicarbonyl compound was generated in situ from 4-acetylpyridine by oxidation with DMSO. Condensation with an aldehyde and ammonia already proceeded at room temperature and in high yield. 1,2-diketones can also be generated from alkynes. Cyclocondensation again yielded the expected imidazole, like in the previous examples. Diketone and imidazole formation from an alkyne may also be achieved in one step. With only one equivalent of propanal, still a substantial yield of imidazole resulted, despite the high reaction temperature and the many potential side reactions. I'll show you now some examples of the conversion of isonitriles into imidazoles. Treatment of aldehydes with a CH-acidic tosmic first yields oxazolines, which can be isolated. Isonitriles are dehydrated formamides and react with nucleophiles like an activated formic acid derivative. With an excess of ammonia, these oxazolines can be transformed into imidazolines, and elimination of toluene sulfinate then yields the final imidazole. A number of tosmic analogues have been described which react in the same way. This here is a typical example of the conversion of an aldehyde into an imidazole by reaction with tosmic. The intermediate oxazoline was isolated and then heated with ammonia in an autoclave. Substituted analogues of tosmic and alkylamines instead of ammonia can also be used, but the scope of these reactions is narrower. Instead of first preparing an oxazoline from tosmic and an aldehyde, tosmic can also react with imines. In this example, a particularly electrophilic imine was used, and the final imidazole was formed in high yield. Interestingly, the intermediate imine was stable and did not cyclize to a pyridoimidazole. Carbodiamides can also react like imines and yield imidazoles when treated with CH-acidic isonitriles. In this example, the initially formed imidazole cyclized once more by addition of an amino group to an alkyne. Acylation of tosmic with acyl chlorides yields tosyl oxazoles, while acylation with imidoyl chlorides, as in this example, gave the expected tosyl imidazoles, without elimination of toluene sulfinate. The same intermediate as in the previous example can also be generated by aminomethylation of a CH-acidic isonitrile, followed by treatment with a primary amine. Amines can add to isonitriles to yield formamidines. In the presence of chloramine T, these are oxidized to sulfonyl guanidines, as in this example. Acid-catalyzed cyclization then yielded a substituted imidazole. Secondary amines with an electron-withdrawing group, like sarcosine methyl ester in this example, can be cyclocondensed with the so-called Gold's reagent. This iminium salt is obtained when DMF reacts with cyanuric chloride. 1,2-diaminoalkanes can also be suitable starting materials for the preparation of imidazoles. Aromatization will require either dehydrogenation or elimination of a nitrogen-bound leaving group. In this example, aromatization was achieved by elimination of sulfinate. Heating nitriles with ethylene-diamine can yield imidazolines. Here, this reaction was catalyzed by an excess of N-acetylcysteine, a non-volatile thiol of tolerable smell. Heating the imidazoline in DMSO for 2 days brought about dehydrogenation and aromatization. Other reagents suitable for this kind of dehydrogenation include oxalyl chloride in DMSO, diacetoxyiodobenzene, and bromotrichloromethane. Alkynes can be transformed into imidazoles by intermediate formation of triazoles. In this example, heating an N-sulfonyl triazole with benzonitrile and catalytic rhodium octanoate yielded first a diazoalkane, then an alpha-aminocarbene, and then an ylide, which cyclized to the final imidazole. Because alkynes are dehydrated ketones, propagyl amines are synthetic equivalents of alpha-aminoketones. Here a propargylamidine was cyclized by heating with an excess of concentrated hydrochloric acid. In this example, an imidazole was again formed by intramolecular addition of an amidine to an alkyne. The required intermediate was generated by addition of a terminal alkyne to an excess of 2-cyanopyridine. The addition of amidines to electron-deficient olefins in the presence of oxidants can also yield imidazoles. 2 oxidations are required, one for the second CN bond formation and one for the final aromatization. Here, oxidation by oxygen was catalyzed by iron and iodine, and the formyl group remained unchanged. In this example, the electron-deficient alkene was nitrostyrene, and the oxygen-mediated oxidation was catalyzed by copper. Here, the imidazoline resulting from the oxidative addition of an amidine to an enone could be isolated. Dehydrogenation to the imidazole was achieved by heating with DDQ. Imidazoles unsubstituted at nitrogen can in principle tautomerize to non-aromatic 2H imidazoles, but this equilibrium lies far on the side of the aromatic 1H imidazole. Non-aromatic 2,2 or 4,4 dialkyl imidazoles should therefore also rearrange to the aromatic isomers, and this is indeed the case. At 250 degrees Celsius, a 2,2 dibenzyl imidazole isomerized within half an hour to the expected 1,2 dibenzyl imidazole. Some spirocyclic imidazoles rearranged even more readily than that of the previous slide, for instance the spiro 4,4 and 3,4 imidazoles. The 2,2 dimethyl imidazole, however, was quite stable, even at 278 degrees Celsius. The 4,4 dimethyl imidazole of this example, however, again aromatized readily when heated to 120 degrees Celsius in DMSO. Aromatization of 2,2 or 4,4 dialkyl imidazoles can also be attained not by isomerization but by dealkylation, as in this example. Here, one trifluoromethyl group was cleaved off from an imidazoline by heating with fluoride and THF. The yield of imidazole wasn't high, though. Imidazoles can also be prepared by reduction of imidazolones, hydantoines and thiohydantoines. These strategies are only rarely used, however, because the starting materials are not readily available, because these reductions are often difficult, and because imidazoles are easier to prepare by other methods. In this example, a thiohydantoine was reduced to the imidazole in 2 steps with a low overall yield. Imidazopyridines, like the product on this slide, are electron-rich, reactive heteroarenes, more reactive and easier to oxidize than monocyclic imidazoles or benzimidazoles. Because of the high reactivity, only few drugs contain these imidazopyridines as substructure. Here, such a compound was prepared by oxidative condensation of a benzylamine with a 2-alkyl pyridine. Let's check some potential side reactions. 1,2 diketones are suitable but highly electrophilic starting materials for imidazoles and are not always readily available. All kinds of nucleophile add to 1,2 diketones and may even cause CC bond cleavage, as in this example. When imidazoles are prepared from ketones or aldehydes, oxazoles are common byproducts. Oxazoles can sometimes be converted into imidazoles by strong heating with an amine or ammonia, but not always. Thus, the best strategy is to prevent their formation by using a large excess of amine and alkaline reaction conditions. This here is an example of the conversion of an oxazole into an imidazole by heating with ammonia in an autoclave. The oxazole was formed in acetic acid, while imidazole formation required alkaline conditions. The condensation of aldehydes with tosmic will also yield oxazoles if no ammonia or amines are added, as in this example. Here are some further references which you can also find in the description of this video. Under the community tab of my channel there's a PDF version of the slides. The next video of this playlist is about the preparation of benzimidazoles. See you!